sets of points. We've done that way back in chapter something or another when we wrote the equation of a line given 2 points. We wrote the equation of a parabola given 2 points. We've written equations of lots of different things given just sets of values. We're going to do the exact same thing here with exponential functions and power functions. And you're going to find that it's very simple. What we're going to do is work with a system of equations, do some quick substitutions, and we're done. After that, we're going to talk about something that's called the logistic growth model. And when we do that, we're going to look at solving the equations with those. It's just a weird-looking equation. And doing some very simple graphing. Now, the graphing with the logistic stuff is going to look awful, but it's like 2 easy steps to do. And this is something that would not take the calculator away from you to be able to do, because you have to have the calculator in order to graph those, because there are real specifics. So let's talk about writing exponential functions. And what we're doing today is we're working with these 2 formulas. We're writing out exponential functions and power functions. What I want you to do is to kind of notice the difference between each of them. When we're talking about writing an exponential function, our variable is the exponent. When we're talking about a power function, it's not. That's the difference between these 2. The exponential function, the variable is the exponent, and the other one is the power function. It's just a little bit different. So what we do here again is that we've got sets of ordered pairs. We're going to use the generic equation. Hopefully write these out a little bit larger for you. So what we do here, the kilowatts and the glare is pretty bad today, is again, we're going to write out y equals a times b to the x. Y equals a times b to the x. And we're going to substitute in x's and y's and leave it in terms of a's and b's. This should look somewhat familiar to when we wrote out parabolas and all that before as well. So we have 6 is a times b to the first power, or 24 is a times b to the third power. Are we okay with that? Just direct substitution? Yeah. All right. Let's take the equation on the left and solve it for a. Let's get a by itself. I get 6 divided by b is a. Do you agree? Mm-hmm. Is it all right that I got rid of the singular exponent for 1? Mm-hmm. Now comes substitution. Since I know what a is, I'm going to substitute in here, and I'll get 24 is 6 over b times b cubed. How can I simplify that?
Can you cross out a b?
Yeah. So you get 24 is 6b squared. Divide by 6. And b is 2.
Oh, and then we'll plus this.
In these, we only have to worry about 1. Okay. Now, what do you think you have to do? So a is 3, b is 2, which means the model, or the equation, would be y equals 3 times 2 to the x. You're done. Don't multiply those 2 values together, because remember when we started talking about growth and decay earlier, we always separated it. Remember, it was always separated as something in parentheses times b to the x, or a times b. We always left it like that. And you're done. Yes, sir?
Wouldn't the 2 be plus or minus?
When we're dealing with these, both the exponent function and the power function, we're not doing plus minus. You don't have to worry about it. Okay, we don't have to worry about it. Is that scary? Okay.
Is that the hardest it's going to get?
Mike, when is it out of the
It's
I
really,
don't know.
you guys are always so worried. It's great.
I didn't get this.
All right. All right, fine. Do one. Write the exponent model here. Again, do this one on your own. y equals a times b to the x. Do this one on your own. I'll give you.
I was like, you found one.
Hopefully, this wasn't so bad.
I wouldn't do that to my.
That took me a while.
Oh, we'll find it tomorrow.
Well, I mean, once you're already on that credit, it really doesn't matter. I don't care.
Hopefully, you got this.
So I'll put another one out there.
You guys get that?
Yeah.
Again, not very difficult.
So on the test, do you want us to actually, like, will it actually have us make the equation?
What do you mean?
Like, the test, like, do you want us to make the equation?
Yeah. No, you always, it'll say write the equations that, write the power equation, or the exponential equation that has the passive points. So let's look at the other one.
You sound like
The power function is different.
Wait, what was that last one?
It's not that different, is it?
This is the first one was the exponent.
Oh.
This one is the power function. The difference here between the two is that now the b value is the exponent as opposed to the x value being the exponent. But we basically do the exact same scenario. We follow through the same stuff. If I have two ordered pairs, again, I'm going to have 5 is going to equal a times 2 to the b. And I'll have 9 is a times 6 to the b. When I take those two equations, get a by itself again. So 5 is going to equal 2 to the b. Substitute into here. So 9 will now equal, what was it, 5 over 2 to the b times 6 to the b. Yeah, exactly. And now you simplify that side, and I'm going to get 9 is 5 times 3 to the b. I don't want to multiply that 5 and the 3 together because the 3 has a b value. So I need to move it the other side. How do I move it? Divide it.
Divide and subside.
And now how do you drop the exponent? Log. What's the base have to be? 3. So that means that the log base 3 is going to equal whatever that value b is. Again, in your calculator, you can type that through. Yes, sir? They don't because they're in the variable. It's an unknown. So when you take log base 3 of 9/5, bless you.
Why not use the?
What was it? Point what? 535, so 0.54.
in short and big numbers.
So your value of b is 0.54, which means in order to find a, I substitute back in here. What do you get for a? 3.2 decimals. So there's my a value, which means now to write it out as the power function, I go back in terms of x's and y's, and y is going to equal 3.43x to the 0.54. And there's my answer. Again, the only real difference between writing out the exponent rule, the exponent function versus the power functions is that with the power ones you'll have to use logarithms to solve. The other ones are, it's extremely straightforward. They shouldn't be, they are going to look kind of nasty. Hit alpha window.
When they're in ball,
No. Yeah, log base. And that comes up just like that. You don't have to hit log first. Hit alpha or alpha. Okay. All right, so let's look at the weird stuff then. Logistic growth functions. What? Now, with all the growth models that we've looked at, the exponential growth, or exponential decay, the growth was continuous. There was no boundary upon it. It would just continue, it would just grow at whatever rate we were talking about. More realistically, if you think about stuff like populations, they're going to level off over time. This is where this logistic growth function comes into play. When you're looking at a logistic growth function, they all kind of look the same. They all kind of look like that. They're always increasing going from left to right. But what happens is that they tail off. Now there's going to be a boundary on the range. Okay? There's going to be a boundary now at the range of these logistic growth models. Again, when we graph these, you're going to have a calculator, but you will need to be able to identify some of the parts. So, for example, the parts for these things, you're going to have two asymptotes. You have horizontal asymptotes, always at y equals 0, and y equals whatever your c value is. The c value is the numerator. Always, always, always. Now, what happens in these growth models is that they're always going to cross the y-axis somewhere. And that y-intercept is always found the same way. You take whatever the value of c is, and divide it by 1 plus a. Again, this value of a is the coefficient before the e in the denominator. When we put up a real example here, you're going to see how very simple this is to graph and plot. All right? Now, the one point from, that you have to find now is the point at which where these things are changing from an increasing rate to a decreasing rate. And that ordered pair, this ordered pair is going to be kind of weird. What happens now is, I'm going to think of this in terms of y. If this is my asymptote and this is my 0, what would be the halfway point? If you're thinking of it in terms of a segment. C divided by 2. Very good. I was thinking about this in terms of if this was a segment and this was like a midpoint to get these two guys equal to each other, this would be the midpoint.
What are you talking about, Mr.
The halfway geometry.
What is this?
It's not Russia, it's an award. What is this, Russia?
Sochi.
This is in double.
Where am I?
Did you see that one girl who wiped out on her snowboard?
No.
Scared. She cracked her helmet.
I haven't really watched any of it.
Has
Has curling started yet?
Does anyone know if Sean White's gonna have that?
Dude, I don't
I'm like tired.
All right. Anyway, what happens here is that this ordered pair is always going to be at the halfway point of your C value. It occurs halfway between 0 and your asymptote for the y part.
Yeah, this is exactly what
The x coordinate is the weird part. The x one, you have to take the natural log of the value of a divided by your r. Again, your calculator will get that for you. And I'll show you an example to walk you through it. It is very, very simple to plot these. Natural log, ln, natural log of a. And again, it's a button on your calculator to go from, all right? Let me walk you through a graph of one of these things. Again, these are rough sketches. If you substitute this in your calculator, you're going to see a real funky looking curve. It's not a big deal, but in order to plot these points, it's all you got to do. So let's look at this. Let's graph this one.
Let's grab it. Yeah, let's grab it.
again, when I start these types of problems out, if I know I'm going to have a whole bunch of different possible variables, you know, A's, B's, C's, whatever, H's and K's, we never did that. We always labeled out all of our possibles. I like to do that because it helps me remember where things are going to go when I substitute them in. Now, again, the reason why I wrote the R value as just 0.5 is because in the generic equation it says that it's negative R, the opposite of R. Just like we would change the sign if it was an H value within parentheses. I treat it the same way. So again, when I go to start this, I know that I'm going to have, I have a y equals 0 asymptote. I have a y equals 6. So my horizontal asymptotes are at y equals 0 and y equals 6. I know that my y-intercept for this case is going to occur at 6 divided by 1 plus 2. So what is that? 2. So my y-intercept is at the ordered pair of 0 and 2. And then lastly, that middle point out here, so that way our curve can go up and change, this point of change, if you will. We take the natural log of 6, we divide it by our r, that's my x-coordinate, and what's my y-coordinate going to be? Oh, did I say, I'm sorry, yeah, it was a, which is 2, sorry about that. And what's the y value going to have to be? 3. The y value has to be 3. Again, do you really need a calculator to plot that point? The horizontal asymptote value is always at 0 and C. Always. That's the rule. Yes, sir.
I find the y-intercept is c over 1 plus a.
Yep. Yeah. Like I said, when we plot these things, you're going to notice it's very, 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 very easy. Now, granted, could you use your calculator to figure out where your y-intercept is? Yeah. Could you figure out with the calculator where that point is probably as well by using your ask function as far as the table is concerned? By using the y-coordinate? Could you kind of mess around with that too?
Yeah.
So again, graphing these things isn't that the world's worst. But I do want to show you something kind of cool with these. No, I want you to solve the equation. I want you to solve that for x.
Alright, then.
What's that? There is a shortcut.
Multiply by 50 or 5. Yeah.
Well, it's one way. Now, guys, if I'm looking at this problem, it is fraction equal fraction, right? What do you do when you have fraction equal fraction? Cross multiply, right? All right.
You defer.
I'll take the kick off in the second half.
So here, if we have fraction equal fraction, let me show you this little shortcut. We're going to get 50 times 1 is 40 times 1 plus 10 e to the negative 3x. Does everybody agree? Who wants to distribute? Why don't you want to distribute?
Why?
No. Well, there's a reason why I don't want it to distribute.
Because that's what you're saying.
Don't want us
Yeah, that's kind of what I'm saying.
Can't I just do that?
Yeah.
Right.
Ah.
Now, guys, what I want you to notice, all I did here was just exchange these two, didn't I?
Yes, you did.
Will.
Yeah, that's the shortcut. If you exchange those two right away, you get 5 over 4 is going to equal 1 plus 10e to the negative 3x. Now it's just a quick, well, maybe a 3-step equation. You all right there?
Right?
Oh.
Did you eat a bug?
What do you have to move first, guys?
The
The 1, okay. What's 5/4 minus 1? 1/4. So can I write as 0.25 for right now? Is that okay? Equals 10e to the negative 3x. Divide by 10. Very good. And now you're left with 0.25 over 10 is e to the negative 3x. How do you undo e? You natural log it. Okay? Now you have the natural log of 0.25 over 10 is negative 3x. Divide by negative 3. Now again, what happens here, guys, it's not that it's a really difficult order of operations style problem to solve for. It's just that you have to know how to type this in the calculator correctly. All right? What I would do is I type in, first of all, the natural log, 0.25 divided by 10, close the parentheses, hit enter, and divide that by negative 3, and there's my answer, 1.23. That equals x. Remember, just go to 3 or 2 decimal places. Let me give you another one of those.
Wait.
You could, you know, if you're rambunctious, you could type that all into your calculator if you wanted. It will work. It's just kind of messy to type.
I love the word random.
If you're feeling lucky. Feeling lucky.
Why do you have pink bag?
You're feeling
So pink.
All right, solve for x.
That's a weird grad. That's
Oh yeah, let's see what it
What's it? Have you ever seen Blackfish?
You guys get that?
Yeah.
Is 1 over 9
scary number.
over 2? Is 1 over 9 over 2 the same as 1 over 18?
Yeah.
Yeah, because I got that too right here.
Yeah. You wrote it because you can type that in the calculator like that too.
Yeah, that's what
Yeah.
That's a natural law.
All right. All right. Let me give you some of these to try.
Wait,
Whatever the decimal is, I don't know.
That's what school does. I think I can challenge you.
Yeah, I'm just buying that.
90.
Too.
No, I got it. Like, I don't know where I'm trying. I think it's good.
Which one is it? Which one?
I don't know.
Where's the one that has the...
Just go with it.
Give those a shot.